Today I am going to deal with the topic Spectrofluorometer. Spectrofluorometer. Learning objectives. Upon completion of this presentation, you will be able to understand what is a spectrofluorometer, the introduction, the principle of spectrofluorometer, what can spectrofluorometer do, the components of spectrofluorometer, fluorescence spectra, and the applications of spectrofluorometer. Upon completion of this presentation, you will be able to understand what is a spectrofluorometer, its introduction, the principle of spectrofluorometer, what can spectrofluorometers do, the components of spectrofluorometers, fluorescence spectra, and applications of spectrofluorometer. Coming to the fundamental classification or the basic classification of spectroscopy, spectroscopy is classified into two types, that is emission spectroscopy and absorption spectroscopy. Emission spectroscopy and absorption spectroscopy. Under the emission spectroscopy, we have two types, that is atomic spectroscopy and molecular spectroscopy. Atomic spectroscopy and molecular spectroscopy. Molecular spectroscopy is the spectroscopy which deals with interaction of radiation with the molecules of the sample. Under this molecular spectroscopy, we have different classifications, that is emission. Under emission spectroscopy, we have molecular spectroscopy. Under the molecular spectroscopy, we have photoluminescence. Photoluminescence is nothing but molecules are excited by interaction of photons of radiation. So, photoluminescence effect. Under the classification of photoluminescence effect, we have the prominent, most important type is phosphorescence and fluorescence. Two types, two categories it is being classified into. It is being classified into fluorescence and phosphorescence. Fluorescence, under the fluorescence, we have the classification of spectrofluorometers. Coming to the history of fluorescence, the term fluorescence comes from the mineral fluorospar. It comes from the mineral fluorospar. Fluorospar is nothing but calcium fluoride. When Sir George G. Stokes observed this phenomena in 1852, that fluorospar, which is calcium fluoride, would give off visible light, fluoresce, when exposed to electromagnetic radiation in the ultraviolet region. When exposed to electromagnetic radiation in the ultraviolet region, this mineral fluorospar would give off visible light. It would give off visible light. Spectrofluorometer. Spectrofluorometer is an instrument which takes the advantage of fluorescence properties of some compounds. The fluorescence property of some compounds in order to provide information regarding their concentration and chemical environment in a sample. So, it makes use of the property of fluorescence property of materials or compounds to provide information about their concentration and chemical environment in a sample. It is an analytical device which depends on fluorescence phenomena, which is a short-lived type of photoluminescence created by electromagnetic excitation. That is, fluorescence is generated when a molecule transmits from its ground state, that is H0, to one of the several vibrational energy levels in the first excited electronic state S1 or the second electronic excited state S2, both of which are singlet states. They are singlet states. The principle of spectrofluorometer. Relaxation to the ground state from these excited states occur by emission of energy through heat and or the photons. So, when an atom or a molecule when an electron gets excited to the higher energy state, it once again comes back to its original state, thereby emitting energy through heat or photons. The difference between this excitation and emission wavelengths is called as Stokes shift. It is called as Stokes shift. Stokes' studies of fluorescent substances led to the formulation of Stokes' law, which states that the wavelength of fluorescent light is always greater than that of the exciting radiation. Thus, for any fluorescent molecule, the wavelength of emission is always longer than wavelength of absorption. The wavelength of the emission is always greater than the wavelength of absorption, which is called Stokes' law. So, this phenomena was observed by Stokes and hence it was named after the scientist Stokes. That's why it's called Stokes' law, which states that the wavelength of the fluorescent light is always greater than that of the excitation radiation. Thus, for any fluorescent molecule, the wavelength of emission is always longer than the wavelength of absorption. Wavelength of emission is always longer than the wavelength of absorption. So, this is a graph which represents excitation and emission energies versus wavelength, and you can observe the Stokes shift there. As I told you earlier, you are drawing a graph between wavelength and the energy levels, excitation and emission, excitation graph and emission graph. So, the wavelength as represented by Stokes' law, what does it state? It states that the wavelength of the fluorescent light is always greater than that of the excitation radiation. Thus, for any fluorescent molecule, the wavelength of emission is always longer than the wavelength of absorption. Wavelength of emission is always greater than the wavelength of absorption. So, in the graph we can see the peak wavelength of emission is 550 nanometers, where that of excitation is only 450. So, there is a difference between the two. That difference is called Stokes shift. That difference is called Stokes shift. What is the fluorescence quantum yield? What is the fluorescence quantum yield? The fluorescence quantum yield phi f, it is represented by phi f, is the quantitative expression of fluorescence efficiency. It is the quantitative expression of fluorescence efficiency, which is the fraction of the excited molecules returning to the ground state by fluorescence. By the process of fluorescence, how much fraction of the molecules that are returning back to the ground state, that is called quantum yield phi f, fluorescent quantum yield phi f. So, this quantum yield ranges from 0 to 1. If it is 1, every molecule in the excited state undergoes fluorescence. As I told, it is a fraction. It is fraction of excited molecules returning to the ground state by fluorescence. So, quantum yields range from 1 when every molecule in an excited state undergoes fluorescence to 0 when fluorescence does not occur. When fluorescence does not occur. When there is no fluorescence, it is 0. When there is fluorescence, it is 1. So, this is the quantum yield. So a molecule's fluorescence quantum yield is influenced by external variables such as temperature, viscosity of the solvent, and pH. It depends on three factors. This fluorescence quantum yield phi f depends upon three external variables, that is temperature, viscosity of the solvent, and pH. Increasing the temperature generally decreases phi f. If the temperature is increased, this phi f quantum yield decreases because more frequent collision between the molecules and the solvent increases external conversion. So increasing temperature generally it decreases the phi f. Decreasing the solvent's viscosity decreases the phi f. Decreasing the solvent viscosity. When the viscosity of the solvent is decreased, your fluorescence quantum yield also decreases. For an analyte with acidic or basic functional groups, a change in pH may change the analyte structure and therefore its fluorescence properties. By changing the acidic or basic nature of the functional groups, your pH value changes and thereby the fluorescence properties also change. So as I have shown you earlier in the basic block diagram, basic classification of spectroscopy in the first slide, we have spectroscopy divided. It is classified into emission and absorption spectroscopy. Under the emission spectroscopy, we have atomic and molecular spectroscopy. Under the molecular spectroscopy, we have photoluminescence, and under the photoluminescence, we have the fluorescence and the phosphorescence. So what is the difference between a fluorescence and phosphorescence? Phosphorescence is emission. It is also photoluminescence effect only. And this phosphorescence is emission of photon when the analyte returns from a lower energy state with the opposite spin. That is triplet excited state. An excited state in which unpaired electron spins occur. And the average lifetime of this is from 10 power minus 3 to 10 power minus 2. Okay. And the average spin is between 10 power minus 3 to 10 power 2 seconds. When we come to the case of fluorescence, emission of photon, when an analyte returns from a higher energy state to a lower energy state with same spin. If it is of opposite spin, then it is said to be phosphorescence, and if it is of same spin, it is called singlet excited. That means the excited state in which all electron spins are paired, whereas all electron spins are unpaired, then it is phosphorescence. And the average lifetime for this type of effect is 10 power minus 9 to 10 power minus 7. 10 power minus 9 to 10 power minus 7 seconds. 10 power minus 7 seconds. 10 power minus 7 seconds. So this is the graph which represents how the electrons are moving from the ground state to the higher energy state. We have from S1, S0 is the ground state, electronic ground state, and you have the energy levels from S0 to Sn, excited vibrational states. The higher states are all excited vibrational states. A is a photon absorption. When it absorbs a photon, it is get excited and goes on to the higher energy states like S2. Then F is the phosphorescence. You can observe that the light radiation, the transition that is taking from S1 to S0, that is ground state, it is represented by F. It is called fluorescence emission. Then we have P, which is represented from T1 to ground state, that is P is phosphorescence and S is the singlet state. Capital T is the triplet state, and then we have IC, that is internal conversion, and ISC, internal system crossing. Okay, so when the electron is coming from the S1 state to the ground state, it emits fluorescence. It emits fluorescence. This is the energy equation and of the energy transition diagram of the movement of electrons from higher energy state to the ground state. What can spectrofluorometer do? What is the necessity? What can it do? It has been used for the direct or indirect quantitative and qualitative analysis of samples by measuring the fluorescent intensity of samples which exhibit this property of fluorescence. It is relatively inexpensive and sensitive. The sensitivity of fluorescence is approximately 1000 times greater than absorption spectrometric methods. This is an emission spectroscopic method. It has been used for analyzing directly or indirectly the qualitative and quantitative analysis of a sample by measuring the fluorescent intensity capital F. It is relatively inexpensive and sensitive, and the sensitivity of fluorescence is approximately 1000 times greater than the absorption spectrophotoric method. Spectrophotoric method. What is fluorescence intensity? I have told you it is fluorescent intensity. It is it gives the measure of the fluorescent intensity gives what it indirectly or directly indicates the quantitative and qualitative analysis. So fluorescent intensity F is dependent on both the intrinsic property of the compound. Both the intrinsic property of the compound, fluorescence quantum yield, that is phi F, and on readily controlled experimental parameters including intensity of the absorbed light I naught, then molar absorption coefficient epsilon, path length of the cell, that is the sample cell, that is B, and the concentration of the fluorophore in the solution, C. So F is F is given by the relation F is equal to phi into I naught into 1 minus e power minus epsilon dc, where F is called the fluorescence intensity, capital F is the fluorescent intensity, I naught is what? I naught is intensity of the absorbed light, epsilon is molar absorption coefficient, B is the path length of the cell, C is the concentration of the fluorophore in the solution, and phi is the fluorescent quantum yield. So F is related to concentration of the sample. So fluorescence intensity versus concentration. When we plot a graph taking concentration on x-axis and fluorescent intensity on the y-axis, we get a graph as shown in the figure. At lower concentrations of the fluorophore, the fluorescence intensity of the sample is essentially linearly proportional to concentration. Up to a certain level, the fluorescent intensity is linearly proportional to concentration. However, when you observe in the graph is up to a certain level, it is increasing linearly. After reaching a peak level, then it again begins to decrease. So, as the concentration increases, a point is reached at which the intensity increase is progressively less linear. Okay, it is progressively less linear, and the intensity eventually decreases as concentration increases further. So by observing the fluorescence intensity versus concentrations graph, we have seen that at lower concentration of fluorophore, the fluorescence intensity of a sample is essentially linearly proportional to the concentration. It is linearly proportional to the concentration. However, as the concentration increases, a point is reached at which the intensity increases progressively less linear, and the intensity eventually decreases as concentration increases further. So the most common reason for this is inner filter effect, that as the absorbance of the sample increases, the light intensity experienced by some of the fluorescent materials is lowered than the experienced by others. When compared to the others, it is lowered. So when excitation intensity decreases, so does fluorescent emission intensity. Okay. When the excitation energy decreases, what happens? The intensity of the radiation also decreases even if the concentration is more, because when the concentration is increasing, what happens? The light intensity experienced by some of the fluorescent molecules is lowered than the others. So the excitation intensity decreases, and so does the fluorescent emission intensity. It is generally necessary to use concentrations that result in absorbent values of 0.1 or lower to observe concentration dependent emission. Then, as the concentration of the molecules in a solution increases, probability increases that excited molecules will interact with each other. They will interact with each other. And lose energy through processes other than fluorescent emission. Any process that reduces the probability of fluorescent emission is known as quenching. So as the concentration of the molecules in a solution, when it is increasing, probability increases that excited molecules will interact with each other, then and lose energy. So they begin to lose energy, and hence the fluorescent emission is reduced. Any process that reduces that fluorescent emission, probability of fluorescent emission, is known as quenching. Other parameters that can cause quenching include presence of impurities, or increased temperature, or reduced viscosity of the solution media. So these are the properties which affect the fluorescent emission intensity when the concentration of the sample is increased. As shown in the graph, up to a certain level it increases linearly, and once it reaches some peak value, the fluorescent intensity begins to decrease, and as the concentration goes on increasing, the fluorescent emission intensity is reduced. This may be due to the probability of fluorescent emission to decrease is due to presence of impurities, or increased temperature, or reduced viscosity of the solution. The optical diagram, this is the optical diagram of a spectrofluorometer. When we observe this diagram, you can understand you have a light source. Generally any spectrophotometer or spectrometer, it consists of a chemical information source. Here you are using a xenon lamp. Then we have the monochromator. Two monochromators are used in this spectrofluorometer. One is the excitation monochromator and another one is the emission monochromator. Then we have, after the monochromator, we have the sample compartment. From the sample compartment, it falls onto the the detector stage, that is nothing but the photo multiplier tube. So we have the light source, then the excitation monochromator, then the sample compartment, then again the emission monochromator, then from the emission monochromator it falls on the sample photo multiplier tube or the photo detector. So this is the optical diagram of a spectrofluorometer. The components of spectrofluorometer are, it comprises of, the first one is your light source. You need a 75 to 450 watts high pressure xenon arc lamp, or lasers are used as the light source. Xenon arc lamp is most commonly used. The first component of the spectrofluorometer is your light source. Then we have the excitation monochromator. Excitation monochromator, then the sample holder. It can be either quartz or optical glass or plastic cells can be used. where the sample is held. Then you have the emission monochromator. Then the detector is usually a photomultiplier tube. Most spectrofluorometers also have a reference sample. The reference is generally a solution of strongly fluorescent molecules with a broad absorbance spectrum, such as rhodamine. Generally, rhodamine is used as a reference solution. The reference is necessary to correct for lamp output, especially when varying the excitation wavelength, and to correct for differences in detector sensitivity. We are going to use a reference solution also for making any corrections, necessary corrections for the lamp output, and especially when varying the excitation wavelength to correct the differences in the detector sensitivity. So, the first component of your spectrophotometer is your light source. We are using xenon arc lamps, the most commonly used are xenon arc lamps. We can also use lasers also. This xenon arc lamps, it is nothing but a discharge lamp, which consists of two thoriated tungsten made electrodes placed face to face with a small gap in an airtight transparent envelope of fused silica or glass or quartz. The envelope or bulb is filled with xenon gas in very high pressure. You are going to fill the envelope. There are two thoriated tungsten electrodes. There is a small gap between the two electrodes. These are enclosed in an envelope or a bulb which is filled with xenon gas, and the gas is pressurized gas. We maintain the gas inside at a pressure of 30 bars. So when a voltage is applied across these electrodes, the gas discharge phenomena starts. The gas discharge phenomena starts in the xenon gas in the gap between the electrodes. So, how does this, when voltage is applied across the electrode, the discharge phenomena takes place. That is, the free electrons in the gas, due to the applied field across the electrode, the free electrons present in the envelope gets accelerated, and they collide with what? They collide with the xenon atoms. Due to these collisions, electrons from the outermost orbit of the xenon atoms, they get detached from their position and come to the higher energy levels. Atoms with electrons of higher energy levels are called excited electrons, and when these excited atoms, they return, the electrons present in the atoms, when they return from their higher energy level to the previous energy level, they release photons. So, the wavelength of radiation that is being emitted through photons is within the visible region. It is within the visible region. The color of the light of the xenon arc light is like the daylight. So, it produces radiation at a wavelength from 200 to 800 nanometers. So, in this way the discharge takes place between the two electrodes present in a xenon arc lamp. So, xenon arc lamp is responsible for producing it is used as a light source in a spectrofluorometer. Then your next part is your monochromator. Monochromators are used to select the desired frequencies from the radiation source and reject the radiations of other frequencies. Okay. Monochromators are of two types. We have the prism monochromator and the grating diffraction grating monochromators. Again, the grating monochromators are divided into two types: diffraction grating and holographic grating. Monochromator consists of the entrance slit, the diffraction grating, and the exit slit. Entrance slit. When we see the diagram of your optical diagram, you can see you have two types of monochromators. One is your emission monochromator and another one is excitation monochromator and another is emission monochromator. In the optical diagram, we have seen the optical monochromator consists of the entrance slit, then the collimating lens or the focusing lens, then we have the grating which is the dispersive media, then again the focusing lenses, and then your exit slit. This is the general structure of any monochromator, components of a monochromator. Okay. So monochromator is generally used in this spectrofluorometer is your grating, diffraction grating is used. Then the next part is your detecting system. Generally photomultiplier tubes are used. We are using the photomultiplier tube. The detection system is your photomultiplier tube. So photomultiplier tube, as you already know about a photomultiplier tube, it comprises of a photosensitive cathode and an anode and several diodes. So photons entering the tube strikes the cathode and it results in emission of electrons. These electrons, what they were accelerated towards the first diode, which is at 90 volts more positive than the cathode. The electron striking the first diode results in several electrons for each incident electron. The process repeats itself from one diode to the next, and after about 10 diodes, each photon results in production of 106 to 107 electrons. The resulting current often needs to be amplified. That's why it is called a photomultiplier. It is being multiplying. It is increasing the number of electrons. So this photomultiplier tube is used as the detector in spectrofluorometer. Spectrofluorometer. Then spectrofluorometer construction. Spectrofluorometers use two monochromators, one to supply selectively the excitation radiation and another one to isolate and analyze fluorescence emission. One is in the first stage. The stage is light from the radiant source. It falls in the monochromator. That monochromator is called excitation monochromator. So one to supply selectively the excitation radiation. And the another one is used to isolate and analyze the fluorescence emission. So the source of light is a 150 watt high pressure xenon arc lamp. So you are using a high pressure xenon arc lamp. Then ellipsoidal mirror collects radiation from this lamp and focuses on the entrance slit of the excitation monochromator. We have an ellipsoidal mirror which collects the radiation from the xenon arc lamp and focus on the entrance slit of the excitation monochromator. Then the monochromatic radiation of specific wavelength is selected by the angular position of the grating. By the position of the grating, you can select a particular specific wavelength. A desired band pass is achieved by selection of appropriate interchangeable slits for the entrance and the exit slits of the monochromator. You can adjust the slit width so that you get the spectral desired band pass, band of frequencies. The radiant energy emerging from the exit slit of the excitation monochromator activates specific molecules. So this falls on the sample. The radiant energy which comes from the entrance slit, which comes from the exit slit of the excitation monochromator, activates the specific molecules within the sample, resulting in fluorescent emission. The emitted radiation, this fluorescent emitted radiation is analyzed by the analyzing monochromator. The second monochromator, that is the emission monochromator, which permits only characteristic sample emission to reach the detector, blocking all undesired spectral regions. This monochromator, it blocks all the undesired spectral regions. It blocks all the undesired spectral regions. When fluorescent light falls on the photomultiplier, the registered photocurrent can be indicated on a microammeter or a recorder or an oscilloscope. Okay. So the resultant fluorescent light, it falls on the photomultiplier. The photomultiplier converts the light energy into corresponding electrical energy, which can be indicated by using a microammeter or a display device like a recorder or an oscilloscope. This is the working of a spectrofluorometer. So this is the equipment which is used for measurement of, spectrofluorometer. It is a spectrofluorometer. The equipment as shown in the figure. You can observe the spectrofluorometer. It appears like that. You have the readout device, the monitor is connected. So the output of this spectrofluorometer, when it is connected, you get the display on the monitor. So fluorescence spectra. Photoluminescence spectra are recorded after the output is derived from the photodetector and it is sent to the display device. You observe a spectra called fluorescence spectra. So photoluminescence spectra are recorded by measuring the intensity of the emitted radiation as a function of either the excitation wavelength or the emission wavelength. The excitation spectra is determined by measuring the emission intensity at a fixed wavelength while varying the excitation wavelength. It is useful for selecting the best excitation wavelength for a qualitative and quantitative analysis. The emission spectra is determined by measuring the variation in the emission intensity wavelength for a fixed excitation wavelength. You're going to, when you are measuring the excitation spectra, you keep the emission intensity at a fixed wavelength. When you are measuring the emission spectra, you are going to keep the excitation wavelength fixed. So this is the graph which shows the fluorescence excitation and emission spectra. When we are plotting the graph taking wavelength on x-axis and excitation and emission, the normalized excitation and emission spectrum, you observe the emission spectrum and excitation spectra and emission spectra. The blue one is the excitation spectra and the green one is the emission spectra. So when you observe the two graphs, you can see that emission wavelength is more than excitation wavelength. So emission wavelength is more than excitation wavelength, and the difference between the two peaks will give you the it is called, as I told, it is called the Stokes difference, Stokes shift, as we have seen in the first slide. In the beginning of our lecture, I have shown you the emission and the excitation spectra. The difference between the peak or the maximum wavelength, it is nothing but steep spectral trails. The difference between the two will give you the Stokes shift. So coming to the applications of spectrofluorometers. There are several applications where we are going to use the spectrofluorometers. Environmental significance. Spectral fluorometers are used to detect environmental pollutants such as polycyclic aromatic hydrocarbons. Like pyrene, benzopyrene, organothiophosphorus pesticides, carbamate insecticides. So they are used to detect environmental pollutants like pyrocyclic aromatic hydrocarbons. Then in the field of geology, many types of calcites and amber will fluoresce under shortwave UV. Rubies, emeralds, and the Hope diamond exhibit red fluorescence under short UV light. Diamonds also emit under X-ray radiation. They are used in the field of geology because fluorescence effects are observed in certain materials, certain calcites and amber in rubies and emeralds also can be identified, and diamonds also emit light under X-ray radiation. So in the field of geology, spectrofluorometers are used. Then analytical chemistry. It is used most widely in the analytical chemistry to detect compounds from HPLC flow. So high pressure liquid chromatographic flow. Detect compounds in high pressure liquid chromatographic flows. TLC plates can be visualized if the compounds or a coloring reagent is fluorescent. If the compounds are so in analytical chemistry also, to detect the compounds we can use spectrofluorometers, where the reagents have fluorescent coloring reagents are used. Then in the field of biochemistry, used generally as a non-destructive way, NDT testing it is called, way of tracking or analysis of biological molecules, for tracking and analysis of biological molecules or proteins. Then possible direct or indirect analysis of aromatic amino acids. Fingerprints can be visualized with fluorescent compounds such as ninhydrin. So fingerprints can also be visualized. So in the field of biochemistry, they are most widely used. In the field of biochemistry, they are most widely used. Then applications of spectrofluorometer. We have the other application, that is other applications of spectrofluorometer is in the field of medicine. In the field of medicine, blood and other substances are sometimes detected by fluorescent reagents, particularly where their location was not previously known. In the field of medicine. Then there has also been a report of its use in differentiating malignant bashful skin tumors from benign. You can also identify skin tumors. You can differentiate malignant and bashful skin tumors from benign. Then in the field of pharmacy, possible for direct or indirect analysis of drugs such as vitamins, vitamin A, vitamin B2, vitamin B6, vitamin B12 and vitamin E, that is folic acids. You can use directly or indirectly analysis drugs such as vitamins, and catecholamines, dopamine and neurophine and other drugs are also can be analyzed. They are used in pharmacy also. So these are the application areas where spectrofluorometers are used. So to summarize our topic of discussion, by now you might have understood the concepts of what is spectrofluorometer, what is the principle of spectrofluorometer, then what can spectrofluorometer do? We have understood what is spectrofluorometer. Spectrofluorometer is nothing but an instrument which takes the advantage of fluorescent properties of some compounds in order to provide information regarding their concentration and chemical environment in a sample. It is an instrument which takes the advantage of fluorescent properties of some compounds in order to provide information regarding their concentration and chemical environment in a sample. It is a device which depends on fluorescence phenomena. That is, fluorescence is generated when molecules transmit from ground state S0 to one of the several vibrational energy levels. That is the first excited level, that is the electronic state, that is S1, or second electronic excited state is S2, both of which are singlet states. So relaxation to the ground state from their excited state occurs by emission of energy through heat or light in the form of photons. The difference between the excitation and the emission wavelength is called Stokes shift, and Stokes law states that wavelength of fluorescent light is always greater than that of the excited radiation. That's a fluorescent molecule. The wavelength of emission is always greater than the wavelength of absorption. and we have an important parameter called what the fluorescence quantum yield. It is called phi f. It is nothing but fraction of excited molecules returning to the ground state. Then we have studied what the spectrofluorometer can do. It is used for direct or indirect analysis, qualitative and quantitative analysis by measuring the fluorescent intensity, capital F, fluorescent intensity. Okay, so it is a very relatively inexpensive and sensitive instrument which can approximately measure, it's 1,000 times greater than absorption spectrophotometric methods. Okay, then coming to the components of spectrofluorometers are, we have the light source, xenon arc lamp from 75 to 450 watts, high pressure xenon arc lamp is used as a light source. Then we have the excitation monochromator, grating, diffraction grating is used. Then we have the sample holder which holds the sample. It may be either made of quartz or optical glass or plastic cell. Then we have the emissions monochromators. Then you have the detector, the photo multiplier, and your these are the 5 parts of your components of the spectrofluorometer. The light source, which is the high pressure xenon arc lamp, is used. Then we have the excitation monochromator, then the sample holder to hold the sample, then the emissions monochromator, then your detector, which is your photo multiplier. We are using a reference solution also to correct any error that is present, to rectify the error. Then the working of your spectrofluorometer is, when monochromatic radiation of specific wavelength is selected by angular positioning of the grating, a desired band pass is achieved by the selection of appropriate interchangeable slits for the entrance and exit slits of the monochromator. The radiant energy emerging from the exit slit of the first monochromator, which is called the excitation monochromator, activates the specific molecules within the sample, resulting in fluorescent emission. The emitted radiation is analyzed by the analyzing monochromator, which permits only characteristic sample emission to reach the detector, which is nothing but the photo multiplier, blocking all undesirable spectral lines or spectral regions. When the fluorescent light falls in the monochromator, the registered photocurrent can be indicated on the microammeter or a recorder or an oscilloscope. So we have observed the fluorescent spectra. The fluorescent spectra is recorded by measuring the intensity of the emitted radiation as a function of either the excitation wavelength or the emission wavelength. When you observe the wavelengths of these two, when you are taking the intensity of the emitted radiation, when we are getting the excitation spectra, it is obtained by measuring the emission intensity at a fixed wavelength while varying the excitation wavelength. You get the excitation spectra. You get the emission spectra by measuring the variation in emission intensity wavelength for a fixed excitation wavelength. So you get a graph which can be observed, and the difference between the two is nothing but Stokes shift. Always the emission spectrum wavelength is more than the absorption spectrum wavelength. Then coming to the applications of spectrofluorometers. Spectrofluorometers are used in environmental, they have widespread applications. The first is the environmental significance, that is, they are used to detect environmental pollutants such as polycyclic aromatic hydrocarbons. Then they are used in the field of geology. Then they are used in the field of analytical chemistry to detect compounds from high pressure liquid chromatographic flow. And they are used in the field of biochemistry for tracking of analysis of biological molecules like proteins. And fingerprints can also be analyzed or visualized with fluorescent compounds, fingerprints. So they are used in the field of biochemistry. They are used in the field of medicine. In the field of medicine, you can blood and other substances sometimes can be detected by fluorescent reagents, and also if there is a tumor, you can differentiate malignant tissues and bashful skin tumors from benign. This can be done. So they are used in field of medicine, and in the field of pharmacy, you can directly or indirectly analyze drugs containing vitamins, then catecholamines and other drugs can be analyzed. So they are having widespread applications. They are used for detection of environmental pollutants. They are used in the field of geology. They are used in the field of analytical chemistry. They are used in the field of biochemistry and in the field of medicine and pharmacy. So with this, we have understood the concept of spectrofluorometer.